Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, good morning, everyone. It's my great pleasure to have Professor Saboa from Rice University, and also his student Patrick Murphy here. So, Professor Saboa is director of the CMC lab at Rice University, and his group does wireless communication algorithms and systems. So he's one of the pioneers on software-defined radio, which is an emerging thing, I guess many of you know. So that's a live demo. So today, Professor Saboa will talk for about 40 minutes, and then Patrick will talk about 15 to 20 minutes. So without further delay, let me turn to Professor Saboa.
Thank you very much, and thanks for the invitation. Thanks for coming today. Actually, I'm just going to get into the thick of things, and I thought I'll give a little introduction of what the center is about, a very quick, super quick overview of different projects, and then zoom into one of them and go into details of that. So that will be the. The center is actually, so Rice is actually a very small university, so everything in Rice is small. So considering that, with that, CMC is actually a fairly big center. It's 25% of the faculty is in this center. So we have 5 core faculty. It's almost 10-year-old center, bunch of graduate students and undergraduate students, and 2 labs. And this is a picture of one of the labs. And then our funds really come mostly from NSF, but we have been for almost a decade working with many different companies in different capacities. So that has been actually very, very great to get the mind share of working with company folks who are actually building actual products. Now, in the kind of research we do, the core research is all about wireless, and together the 5 of us really cover different aspects of wireless. Okay, so we go from information theory analysis and foundational analysis, communication algorithms, to network protocol designs, of course, and building actual hardware. So looking at very low power, highly efficient, high throughput hardware for these things. And more recently, I would say in the last 4 or 5 years, we've also added another component of building actual prototypes and deployments. So actually trying to do at-scale experiments of wireless networks. So I'll actually give a super quick version of 4 projects. You will hear about 2 of them today. And the first one, which is actually something which was born out of Rice. It's called cooperative communication. So it was actually, the idea is very simple. There are multiple laptops or multiple mobile devices, wireless devices in any given geographical location. Instead of only competing for resources, they can actually cooperate with each other. And this cooperation is actually at much shorter time scale, at symbol level time scales. Okay, so this is not at a packet time scale, it's not routing, it's actually even deeper than that. And in this case, for example, in this picture, the cooperation is using this link which is there between these 2 nodes all the time. So wireless being a broadcast medium, different nodes can overhear each other. How do you exploit this link? So information theoretic bounds tell you that there is a capacity benefit to doing this. And then there are protocols. And more recently what we've done is actually gone ahead and built an actual symbol level cooperative system, which Patrick will actually explain a little bit more about. And that's where the prototypes would come in. The newer project, so we actually for cooperative communication, we've been at it for a few years, so we understand it a little bit better. But the newer thing which we got started in the last year or 2 is on the dynamic spectrum management. So I think which is actually quite actively studied at Microsoft. We've been reading papers from folks at Microsoft. And the idea of cognitive radios, or actually how do you use secondary leases in the licensed spectrum, or actually distributed access, which is what I will talk about in unlicensed bands. Okay. As I said, all this, our focus is always to actually build these things. So there is a fair bit of effort of building high-performance architectures to actually implement any sophisticated signal processing or coding algorithms we come up with. Okay, and then of course doing a power management at a higher scale. So many of these ideas actually come together in a mesh networking project which we started in 2003. And there, I mean, being in research, it allows you to be fairly ambitious and naive at the same time. So we decided we're going to do a complete clean-slate design. And the reason for doing that was that mesh backhaul, which carries the traffic down to the last, the gateway node, is not governed by any standards today. So it was an opportunity for us to look at a completely clean slate design of physical layer, MAC layer, routing, everything combined together. So we actually decided to take that project, and simultaneously, we actually started our platform development in two directions. First, we wanted to understand deployment, okay, and there we got lucky. We ended up partnering with a nonprofit organization called Technology for All. It's a Houston-based organization, and the idea is to empower low-income communities to be to improve their quality of life. So this Houston community is fairly low income. It has like less than $25,000 per capita income per household. And Technology for All has been running programs for a while now where they use technology. They train them, the kids and their parents on computers, give them free computers to actually use for education, to actually generate income at home. But the community has no internet access other than dial-ups. Okay, and most of them really can't afford even a dial-up. So they really wanted to somehow provide them internet access, and we ended up partnering with them. And since 2004, we have actually managed to deploy a fairly reasonable size mesh network, and this is built out of mesh boxes which are just .11 cards in them. But the neat thing is that it covers a fairly big area. It's around 3 kilometers square at current moment, and has more than 2,000 real users. So this is not simulated traffic or graduate students running around with laptops. It's real users whose only internet source access is this network. Okay, so that has been great for us to be able to do such large scale, such large scale data. Okay. Another thing is that now that we understand deployments, we are now thinking of how do we increase throughputs in mesh networks. We understand the fairness issues and throughput issues a little bit better. We are now actually the hope is that we're going to actually try to replace these mesh boxes with custom mesh boxes based around that platform. Okay, and that's what you will hear more from Patrick on, is an open source project which allows you to build completely clean slate, absolutely new from ground up protocol stacks. You can change the physical layer, MAC layer in any way you want. And these nodes are small, fairly small, they're deployable and self-contained. So that you don't need to actually have a laptop sitting with them to make them work. Okay. So we made this project open source. We got the some parts. We're actually selling the hardware in small quantities. And it's in use in some places right now, and then more folks have actually have ordered stuff, and we're building them slowly. Okay. So that kind of gives you a picture of the activities we do, go all the way from theory to actually building stuff and even deploying them to study all aspects of wireless communications. And as promised, I will drill down into one very small sub-problem we're looking at, which is that of distributed spectrum access. So I'll take hopefully 40-ish minutes to go through this first part, and then Patrick will take up another 15 minutes to follow up on the hardware side of things. Okay. So the context for the problem is, which is actually fairly well understood, is just if you talk to any wireless designer, they will say there's just not enough spectrum to build new commercial services, especially if you want high throughput. Okay. Now, which is true if you look at the FCC map, but it's not really true if you look at the actual usage. So FCC has sponsored study, and I'm sure folks in the room are quite well aware of it, that a large portion of allocated spectrum is unused at any given time. Okay, so of course the natural conclusion is there is lots of spectrum available, just not used very well. So it's not really about spectrum; it's all about spectral efficiency, how well we use it. Okay, so that I guess discovery was important, and that has really given new ways of allocating spectrum. So there is TV bands, or analog TV bands are going away, and they're going to be auctioned soon. And for folks who don't know, actually Qualcomm quietly bought one 6 megahertz TV band a few years ago. And there is actually only one TV band available in the US, which is available in every city, was not being used in every city in the US. And so they are actually using it for media flow, where they're actually just sending real-time TV broadcast over that 6 megahertz band for mobile devices. So I think some of the ISPs are actually companies that actually already started using it, selling that. Then there is this idea of secondary markets, which I think FCC has already put in place, where the cellular band licensee can actually resell their bandwidth. Okay, and so companies like Nokia's and Verizon's are actually looking into making extra money by real-time short-term leases to secondary services. Okay, so that's another revenue generator where you try to keep the spectrum as busy as possible, as heavily utilized as possible at all times. Okay. Now there is a third opportunity, which is there's a potential for new unlicensed bands. So 2.4 gigahertz, which is a fairly popular band, is now quite crowded, and it has lots of other devices beyond Wi-Fi, which I would just label them as dumb devices. They are just microwaves and things like that. Okay. So and there are not that many microwaves in the world, so I mean it's not that big a problem. But if we really want to ensure that the new bands which we open up, the unlicensed band, we want them to be used as efficiently as possible. So that will be the discussion of the context for today's discussion, that if we had a new unlicensed band, how best possible we should use it. Okay. So the scenario will be very similar to what we have today, right? We will have a chunk of spectrum given to us. We will channelize it in some arbitrary fashion into beef bands. And we won't specify how big these bands are and should they be equal or not. But for all purposes today, they will be all equal. And then we will have k, single hop flows. Okay, they could each be a different network, different set of devices, Bluetooth versus Wi-Fi type of differences, or be parts of the same network. Okay, and we won't really care about that all that much. So what would be the driving goal would be a peaceful coexistence, that we want these devices to get along. But we will make sure that whatever we do works in heterogeneous devices. That means, as I said, there could be different services which are deployed once or services which are deployed in future. So we will, and a lot of these different device or standards are really, they're one of the distinguished factors is transmit power. What is the range of communication? Okay, so we'll keep transmit power in the picture all the time. And then the other place where there could be heterogeneity could come in is bandwidth usage. That how much of this total available bands they use at any given time. Okay, so if you want to build super cheap device, you may not want it to scan the whole band. You may just want it to pick up smaller subbands. Okay, so the picture might look like this. There are some flows which use larger portion of the bandwidth potentially, or can use larger portion of the bandwidth, and some flows cannot. Okay, so that's another place where you will have heterogeneity in the network. Okay, so the thing which we will as one of the design goals, we will assume we'll kind of continue with the same model of development of unlicensed band, that there is no centralized control to start with, there is no manager of networks. So there is no network of networks kind of manager in here. Okay, so each network manages itself, and then they somehow has to coexist with other contending networks in that particular bandwidth. Okay, and true to our philosophy of trying to build these things, we will keep that there is no knowledge of topology, there is no genie available which gives us this, and there is no channels can change randomly in a wireless setting, and you don't know what other flows are really doing. Okay, so we will really start with no knowledge in the system. Okay, so with that, basically the flows somehow have to make independent decision about their choices of the bands they use and the power they use to actually transmit. Okay, so the independent decision making would be an important part of the whole thing. Okay, so first let's look at so I'll kind of divide the discussion into two things, and the terminology, the nomenclature will become clear as we go along on passive control and active control. So let's instead of drawing that picture with flows, I'm going to actually just live with an interference graph. Okay, how different flows affect the other flows in the network. Okay, and the interference graph has a little bit more information than just connectivity. It has information. The nodes are a little bit bigger if a particular flow can use larger amount of power. So the size of the node represents the amount of maximum transmit power that flow has available. And then the edges are thicker if that high power node can cause higher interference to other nodes. So it's an asymmetric directed graph. It's a directed graph, and it's not necessarily symmetric, and primarily because different nodes could have different amount of transmit power in this system. Okay. So with that in mind, so that will be our first protocol skeleton. So what are we after? We're trying to find each of these nodes a good band for operation. Sure.
About the model, the previous slide, you've modeled the networks as one node, like two actually have a transmit and a receive, and the interference at the transmit and the receive
is not symmetric. Yeah.
Yes.
I'm hiding away from that right now.
Okay, that's fine.
Yeah.
But that's also purposely done just to simplify the model.
Just purposely done. Yeah. And actually, that's a non-trivial problem. So I will kind of just mention as actually ongoing work to address that. Absolutely. So the protocol skeleton, the first protocol skeleton would be very simple. It's just a sense and adapt scheme. Okay. So the idea is that each node, each flow. So we're no longer going to. The smallest entity is now a flow, and we're going to assume that somehow the transmitters and receiver in a flow can keep synchrony and have some common information. Okay. So there is a cheat there for sure. Okay. So but somehow these flows are going to sense interference, the level of interference they see in a band, and then they would decide whether how useful it is to be in that particular band B. And then they will just hop around till they find a good band to operate. Okay, so remember we are starting with no information. So learning is an important aspect of this whole thing. They will have to do some sensing, figure out how much interference I face, how bad the conditions are in the band, and then based on that, choose their next action. Okay. So let's fill up this, and my slides seem to have hung up. Oops. Yeah. Okay. All right. So we basically it's a passive sensing network. That means all it can sense is what's being transmitted without and so essentially it senses the amount of interference. So each flow makes an estimate of how much interference it's seeing in a particular band. Okay, and since this is going to be an estimate, right? It's basically based on a finite time sensing when other flows may or may not be active in that particular band at that any given time. Okay, so based on this particular estimate of interference, it makes it estimates how much utility it could derive out of this band, and that's just it uses a utility function which gives it an estimate of maximum possible throughput in that particular band. Okay, and that's just a usual log formula for finding how much throughput you could get out of information theoretically how much throughput you could get out of a system. And there all it is doing is looking at its using its maximum power and the estimate of interference to find out what signal to interference plus noise ratio is. And that gives it an estimate of utility it could derive out of that particular band. Okay. And then when I say it will hop around a little differently. Okay, then the idea would be that because all this is based on estimates, you really cannot commit to any particular band a priori. You can't just base your decisions on one estimate because you may have gotten a very inaccurate estimate at that instant of time when other bands were also hopping around. Okay, so what it will do is it will assign a probability of usage of every band. Okay, so it will basically bring soft decisions in this whole process.
So expectation for UKB is with respect to the interference statistics?
That's right. So you have some statistic of this essentially, and essentially you're treating it as a Gaussian noise. Actually, yeah. And then what you would do is based on this probability per band, you can actually form your net utility. You can derive from the current assignment of bands. Okay, so let's say you could assess 3 bands, 1, 2, and 3. In band 1, you may assign 0.7 probability at some given point of using it, 0.2 of using band 2, and 0.1 or less of using band 3. Okay, and then these are the probabilities you're going to be adjusting based on your measurement of interference as you go along in this iterative scheme. Okay, so the reason you don't commit to anything immediately is because everything is all your decisions are based on estimates, right? There's nothing you have exact information. Okay, so that will be our protocol, which we'll call the sense and adapt protocol, which is very similar to what actually some devices do today. Like Wi-Fi devices kind of do this in some sense. Okay. And then some mechanics further mechanics to actually complete the picture. We're actually assuming that these devices are half duplex, that they can either sense, basically either receive or transmit. Can't do both simultaneously. Okay, and that's actually very true of most hardware. So we will actually assign a probability to sensing also. That means at any given time, a flow has to make a decision: should I send data or should I sense? Because they are mutually exclusive operation. So you will actually assign an additional probability of sensing in addition to probability of choosing a band to send. Okay, so your probability vector is now a little one dimension longer in this case. And then once you have done this, the update process follows very standard tools. Does a gradient descent, based on the estimated gradient, and the gradient is essentially the derivatives of utility with respect to the probabilities you are actually trying to optimize. Okay, so whenever you have an iterative scheme, the questions are, of course, does it converge? And if it converges, where does it converge to? Okay. Now, in this case, there is no power management going on, right? So actually, the nodes are always blasting at full power, and there is a reason behind that, why they have to kind of do that. And anyway, when they do that, what you find is basically this whole thing converges to some competitive Nash equilibrium. Okay. And Nash equilibrium is a point where, if there are multiple entities fighting for a resource, is a point where changing your resource usage will actually hurt somebody else. So you really nobody can have a win-win situation by changing it from that point. Okay. So what does it mean for our case? If you look at our network and you have 2 bands to work with, okay, so there are 4 flows and 2 bands. So the problem is only interesting if there are more flows than bands. If there are more bands than flows, then you can just assign them a orthogonal band and we can all go home. Okay, so if you have only 2 bands to operate, and if you use this sense and adapt protocol, okay, what it does, it essentially pushes. So this is the user which has a large transmit power, causes a lot of interference. It essentially pushes other users away to a different band, and then occupies. It creates so much interference for them that it decreases their utility of using that particular band. So they essentially go crowd in one particular channel. Okay, so it's not exactly a very good solution, because really it's a very selfish equilibrium. Rich gets richer. This node, which had a large transmit power to start with, was potentially getting a higher utility. Right, its power was higher. Utility depends on your own transmit power, and it became even better because it drove all the interference away. It drove all the potential interference away. Okay, and so it's really very similar to what any passive sensing network would do today. If you actually try building some of the interference sensing nodes, you will actually get an unfair equilibrium. Okay, and that's unfairness. For example, in Dart 11 is very well not multi-band, but actually just unfair allocation. It's quite common.
So here the 2, 3, 4 are on the same band. So are they always transmitting concurrently?
Yeah, they could be.
Can they figure out some ways to timeshare?
So timeshare is just one of the policies which you can do. Yeah.
So in your analysis, do you?
No, there is no difference between that, because you're essentially allowing it to use any. It actually uses. You can think of it using codes based on what interference it senses. So it lowers its rates if it sees more interference, but they can actually have concurrent transmissions.
But if they concurrently transmit, they will cause interference to each other, right?
They do, yeah, they do. So the model here is actually of completely backlog traffic, which is always sending in some sense, right? So it's actually not the whole protocol doesn't really go into the mechanics of how these transmissions are occurring. Okay. So again, that's another important detail which is not being counted here.
Kind of a related thing.
figuring out time slots as figuring out. I mean, you're talking about bands like they're just fixed slots.
They're fixed, yeah.
So, I mean, on one problem is that, well, if you don't have enough users compared to the number of bands, then all these other bands go unused.
Unused, yeah.
And the other problem is if you have too many users for the number of bands, then you have to collide like this instead of saying shrinking the size of the band.
Right. Yeah. So actually, the thing is, so I think what I want to get at is in this, if it was a loaded system, okay. So in a lightly loaded system, the problems are slightly different, and without having thought about it, I would say they are slightly less hard. I mean, they're I would say they're not that hard. Okay. So let's look at where you have more users than you can potentially support in some sense. Okay. What I want to get across with this sense and adapt protocol or passive sensing is that no matter what level of adaptation you allow, because you have no way of estimating other flows utility, you actually always end up with unfair allocation. So I want to go back to the goal of peaceful coexistence. So in a sense, I'm translating that peace as fair allocation. Okay. So what I essentially want to say is that no matter what you do, how much degrees of freedom you allow it, that the flows have no way of adjusting to be socially, good to each other. Okay, so even if you allow different bandwidths, they may not know actually how much bandwidth to use unless they have some sense of how much bandwidth you are trying to use. Okay, so unless you have this information, you really cannot actually do anything about it. So that's actually the only message which comes out of this analysis is some sort of active sharing, and that's where we'll go next. Okay, so really that's actually the main reason and the main conclusion of this whole thing is that unless you find a way of estimating others' utility, you really cannot do anything other than be greedy, right? You won't reduce your power without knowing anything about other users. You don't want to hurt yourself unnecessarily. Okay, so actually this great discussion is kind of leading to the next part, which is what I will call an active network, where nodes actively broadcast something about their utility, and I will give some details of what that broadcasts are. Okay, and then the neighbors essentially hear the broadcast, and then they use it to adjust their behavior. Okay, and throughout in this whole analysis, in the previous part too, we are essentially assuming asynchronous operation. So different networks are not synchronized in any manner; they're just operating themselves. But once in a while, they will broadcast something. Okay, and the key assumption here is that, or is the key design requirement is that these broadcasts are understood across networks, essentially across flows, and I think that's kind of an important part which will come out here. Okay, so that's the first part of it. It's essentially, when you do a broadcast-like approach, you really are not doing any per flow interaction. Everybody just broadcasts. It has no knowledge of topology, who's going to hear the broadcast, and you really don't need any topology information in this case. Okay, so that's why we labeled it connectionless. You never form connections with anybody else other than you want to transmit data to. Okay, so the last piece is the behavior control, right? So now, of course, the flows will control their band of operation, but now we will be able to control something more. And in our case, we will control, because we can't change bandwidth, so we only given one parameter for, but you can easily adapt it to that case. But you will only control how much power they transmit. Okay, and basically the way we'll control it, that if this is your maximum power you could transmit for any given flow, then you can actually scale it by a number from 0 to 1. So 0 meaning you will completely shut off, not send anything anytime. 1 meaning you still blast with your full power, and anything in between. Okay, so here is our the protocol skeleton in this case. We will still be sensing interference because we're going to estimate utility based on the interference, but now we will be actually sensing broadcast too. Right? So that actually adds the active information you get from the network. Now what that will do is it will allow us to estimate the fair share you should get from that using that band. Before we could only estimate the utility I could derive myself. Now you can actually, once you hear something about your neighbors, you can say, in relation to my neighbors, what should be my fair share in the network? And then you essentially hop around, do this iterative process till you basically, your utility matches what your network objective is. You kind of converge to the right utility point. So again, let's fill in some details in this. So you're now just, of course, sensing the interference like in passive sensing case, but you're also transmitting. Each node picks up its favorite band. So you remember it has assigned probabilities to each band. It picks up the band which has the highest probability at that given time, transmit that band index, and the maximum utility it could derive, which is basically using his full power in that particular band. So it gives a sense of what's the best it could do at any given time. Okay. So once this broadcasts are heard, you of course first compute your own current utility, which is based on just your log SNR formula or 1 plus SNR formula. But you can also actually estimate what the fair share should be, because now you can have a sense of what other users' utility is in that particular band based on the broadcast. Okay. And that allows you to actually compute essentially a maximum like fairness criteria, right? So you can actually compute what your utility in that band should be, how you should decrease it. Okay, and there now when we hop around, you not only adapt the probabilities which you assign to each band, but also the transmit powers, the transmit power gains. So you can now scale your transmit power. Okay, and the way you scale your transmit power intuitively would be so that you reduce your selfish utility towards the fair utility point. Okay, so yeah, go ahead.
Like one question is how if you don't know the topology of like if I'm a flow and I can kind of overhear what my neighboring flows kind of do or want to do, but I don't know how they are mutually interconnected. So how can I like
you only estimate your neighborhood basically. Everybody is only getting an estimate of your neighborhood.
But it could be that this is not. It could be that this is suboptimal. Assume that I don't know.
Sure.
Maybe I'm not
yeah,
understanding.
Yeah.
So maybe I have two neighbors, but they are not neighbors, like for each other. So now, if I interpret this correctly, then I would say, well, maybe roughly my fair share would be to take 1/3 of the spectrum, but in fact I should take one half because,
absolutely.
or could potentially.
Absolutely,
take
you're absolutely right on. So when you actually do this, you're not guaranteed optimality, the highest spectral efficiency. You're not guaranteed that. And that's, I think, the problem. You're still operating with local information. So unless you have a network-wide information, you can't have a network-wide global solution. I mean, a globally optimal solution.
You could.
I mean, at least that's why. I think pretty much every solution I've seen assumes something about the network which has some component of global information. Like some of them would assume, I mean, different papers, and like the chromatic number is known, for example, right? You know what's your maximum edge weight and things like that. So something about the graph is known, which is actually a global property.
Well, essentially, I think it's more of a trade-off of how much local information you have, the better your solution can be. So, for instance, if I have no information about the global properties, but I know like all the interconnections of my neighbors, then that might already help me.
Help me a lot, yeah.
But if I get 2 neighbors, I can do more.
Absolutely, you're absolutely right. Okay. Okay. Yeah. No, you're absolutely right. So actually, that's why the problem doesn't, all the statements you make in this actually never make a claim about the optimality of solution. In fact, that's just almost, Nash equilibrium, or even in this case where we converge, is never guaranteed to be efficient, right? And there is a price of anarchy and all those, so there's a fair bit of work on that. So, so again, the gradient descent, I'm actually not going to put any details because in this case the gradient calculations are even more complicated than the previous case. So, but if you're interested, I can send you this paper we just submitted. But again, the idea is you're essentially some gradient descent algorithm where you're now updating your probabilities and also updating your transmit powers based on what you have learned from your environment. Okay, so the result is that this protocol, which is now updating the probabilities of using a band and also the transmit powers in those bands, really converges to a per band maximum fair solution. Okay, and I'll explain what that means. What does per band means? Okay, so if you consider our earlier example, this would, with the 2 bands, this is how the final allocation would look like. That in this case, if just as a contrast, the selfish case was where the stronger user pushed everybody away to a different band, In this case, actually, the weaker user is actually getting a better treatment. It gets a band for itself. And it pushes other medium and strong users, in this case, away in the second band, where they all work together and do a power control. Okay, so in this case, these guys, flow 2 and 3, are still using their max power, while flow 1 has reduced it to match the power and match the utility of the other flows. Okay, so this is how actually the go ahead.
So generally, when you're doing this, then do you get a lower total power for the entire system being used? Is that kind
Could
of
be, yeah.
emergent property of this whole thing?
Yeah, but it may not actually mean lower throughput though.
No, but
Yeah.
the total power of the system looks like it would go down.
Yeah, yeah. And that happens quite often, especially with high asymmetry. Yeah, definitely.
But that's not part of your constraint.
It's not.
It's not, no, it looks like it just
It just, yeah.
becomes.
It becomes that way. I mean, especially if there is a lot of, if you have fewer bands and many users, and then some users are, high power, low power. The high power will have to come down. The maximum fairness will bring it down, just to meet the utility. Okay. Now, the thing which I want to point out is that the utility which flow 4 derives is actually different from the utility which these flow derive. So they are not. There is no equality of utility across bands, and there is no reason to do that. In fact, right? You all want is that when you are there, you get the maximum possible utility in some sense. So if flow 4 was operating by itself, which is what it is doing now, this is the best it could do anyway. But you shouldn't hurt. Just because you have a very low power user, you shouldn't hurt everybody else by bringing them down to its utility. So it's not a global maximum, it's just per band maximum solution, a fair solution. Okay, so kind of intuitive in that sense. So it's actually a fairly general result. Really, there were there were some cheats which you guys identified very quickly, which was great. But there is another cheat actually. So okay, and there is another one which to prove that theorem, a maximum fairer solution, you actually have to assume that the broadcasts are heard error-free and you never miss a broadcast. Okay, and there is a reason for that. Essentially, the reason goes back to our earlier discussion that how can I compute a fair share unless I hear something about the network? Similarly, if you want an exact maximum fair solution, you want to have exact utility numbers for other flows to get an exact maximum fair share for yourself. Okay, so that's why these things are error-free. So that means at any given point, each node has the right idea about maximum share of other nodes too. Everybody's computing the same thing. Okay. So the thing is, so if you actually have errors in broadcast, which is what will happen, right? Some broadcasts will be lost to collisions. Sometimes if you're not listening in the band and stuff like that. There is no reason to actually. There is no way, at least we can think of, you would get a maximum fair allocation, right? Because nodes, even if they don't want to be selfish, really have no way of avoiding errors in their computation of utility. Okay, so you really won't converge to a maximum solution unless you have some perfect knowledge. So the perfectness of knowledge is actually very important too in any solution, and that's actually very hard to impossible to guarantee in wireless systems. So it actually kind of hinting towards that maybe perfect fair access is just not possible. I think we should shoot for something lesser than that. Okay, and then I'll just hint on what that lesser might be, but we haven't actually figured out those results. Okay, so just a different picture of how things evolve. Because it's an iterative solution, and I always actually only talked about the equilibrium points. If you have this is a little bigger topology, which we just took a random topology of 10 flows, and actually all 10 flows have different powers. 10 random powers. Only 2 bands to work with. And this is your, the first greedy, selfish protocol, where you can see actually, it's actually converging to 9 different utilities. So some flows are getting very low utility, and other flows are getting very high utility, and for some reason 2 flows end up being in the same utility. Maybe they have very close powers, or the topology was they were away from each other. Okay. So this is a selfish allocation. It just goes all over the place. There is no fair. If you actually use the active protocol, in this case, all flows actually end up converging to the same utility. And so just be lucked out. Yeah. It's just iterations actually. Yeah. Should actually label it better, but yeah. It's a very slow converging protocol, as you can see. It's like 10 to the power 5 iterations or something. And if you make the problem a little bit more interesting in the sense that you actually increase the number of bands, then what what I was hinting towards, that you get per band max-min fair solution. Okay, so if you increase the number of bands, you can see the lower power users are actually getting their own bands, and they're the ones which have maximum utility is lower. However, the higher power users are now crowding into 1 or 2 bands, I think 2 bands in this case, and then matching their utility, managing their power to actually get to the common utility. But you can see the higher power users have a higher utility than the lower power users. They are not being brought down, pulled down to match the worst user in the system. Okay, now, so we did simulate to get some idea, to actually form conjectures of what happens when you have errors in broadcast. Okay, so there was a very simple model that at random some broadcasts were dropped. So it's like you can think of it erasure channel model. Okay, and it kind of does what you would think it will do. Basically, depending on the deviation. So the conjecture which is forming around is that depending on the error in the list, your information about the broadcast. Let's say if there was an epsilon error, then you would get a deviation from the max-min fair solution, which is bounded by in a certain sense. Okay, so that's where we are actually trying to show is that you can't really get max-min in that case, but you can be within a bounded distance from some max-min solution in this case. And that's what actually most of our simulations really point to, that still you get the same behavior that some of the weak users are actually getting, if their error in estimates of utility was small enough, they still get their own band, but then other users are now hopping back and forth. Okay. Now, in terms of, it really has some, as I said, all this analysis is only the beginning of the story. It's not the end of the story, right? Typically, that's just true for most analysis, simplified analysis. Is really what we are leaning toward. If you want to actually build this, we really need a common packet type, a broadcast which is understood by every flow in the system, and I hinted that. So it has to be some sort of a universally accepted format. And I think this has been proposed in some sense, and this is actually building another case for it. That if you want fairness across networks, you got to agree on something which everybody understands. Okay, and that's the common broadcast packet. Okay. Now, what that really contains is still under the point of some discussion. We gave one example, and that what it contains really depends on what utility definition people would agree on. And I am not a fairness person per se. I'm a more information theory. So everything is fair in information theory. But really, it actually depends on your philosophy of sharing. Okay. So that's again a point of discussion, whether max-min or proportional fair is. But really, if you want to implement it, which is what a lot of you gotta have something which is simple and efficient. Really can't think of another chip which computes just utilities. And in terms of building this system, the adaptation is not that hard. For power control is a well understood problem. It's there in almost every system. Fast band skipping is actually very easy. We can do this in this hardware. You can skip band very quickly. However, the problem the gentleman here pointed out is very hard, where you actually have to keep synchrony in skipping band across transmitter and receiver. Okay, in face of interference. So if the transmitter decides to skip something, then the receiver has to follow it. That introduces delays, which is, for example, are not accounted here at all. So that is not very well understood. What is the shortest time scale you can do these things? But once we actually understand that, we can actually then account for the cost of skipping in such an analysis. Okay, so I'm just going to recap, kind of stick to my promise of having a 40-minute presentation. Basically, what we looked at today was a very special case of, trying to do a peaceful coexistence of devices, potentially heterogeneous, and doing a distributed control of networks, essentially across networks. So we do look at a simple passive sense and adapt control protocol, which is simple. Just nothing new required of the devices, but unfair. And then we essentially kind of looked at, which created basically the need for doing an active collaboration, and allowing us, giving us a tool to actually enable fairness across networks. Okay. So I can take some questions if there are more, and then.
There's another question on the model. You used the Shannon-like utility. Have you thought about using the outage capacity instead? A lot of folks out there in the Information Theory Society, when they look at fading channels,
right,
they prefer
Right.
the outage capacity.
Right. Yeah, I think we haven't, but it's not a we could, I'm not. I think it behaves the same way. I think it is is a good utility function, in terms of its convergence. Yeah, definitely. So the proofs actually don't really require any special property of that utility function. It's a very standard proof technique. It uses certain properties of utilities, and then you can actually that function satisfies all the properties of that utility function.
What kind of networks were you looking? What made you decide that it has to be distributed and not coordinated? Because you gave the example of the mesh backhaul, which is easily a coordinated network.
Yeah, that's true. So mesh backhaul was not our motivation actually. So mesh backhaul actually is, if we ever implement, would be something like this. Would be actually in fact very, very planned network, and maybe for all reasons it may be even fixed frequency assignments or fixed at a fairly long time scale. So the motivation here was devices which are not part of the same network. So Bluetooth versus Wi-Fi, that kind of devices, rather than devices of the same network, which you always, I think, or not always, but we typically make them a managed system.
So I'm wondering how realistic the common packet format, and you need more than just a common format, common way of communicating it, like from a common channel, common modulation and encoding, and all this stuff.
Actually, a lot of time, if you look across most of the popular standards, it's not that hard. The commonality looks hard when they're built, rather than it's not a fundamental. So the one good thing which is happening, if you look at it, most of the things are becoming OFDM multi-carrier system. Even the modulations are actually now gravitating, and the reason is that the devices are getting wideband, and they're all using wider and wider bandwidth. So if you look at wireless USB, which goes 500 megabits per second, and is a very short range 2-meter type of communication system, and in fact it is even I've seen demos at 1 gigabits per second of wireless USB. They're all using multi-carrier communication. If you look at wireless LAN, already uses it, an OFDM system. So in terms of physical layer formats, the modulation, 4G, 3G, there are many systems that are actually gravitating towards a very common. So it's not a very hard to actually come up with a packet which does a common modulation, in my opinion. I think it's mostly political reasons that it doesn't happen, not technical reasons.
So would you designate one little tiny band, one of those channels?
You could, yeah.
There's a common channel.
And that could be a broadcast channel. It's very easy to do that, I think. We all know technically it's very easy to do that. We can go back and program this thing on many different pieces of hardware. You can do. I think it's, as I said, standardization committees are not, they operate under different. So.
I think the work, this is very interesting work. I appreciate it.
Thanks.
I think a lot of it can be applicable to the new band, 3650. If I look at your model, you have distinct flows, as you call them. There's a band that's been allocated for more or less cognitive use.
I see, yeah.
Quite interesting.
Yeah.
So we can communicate offline if you want.
Absolutely. So, go ahead.
Done any analysis like security? I'm always thinking security. So you're trying to find peaceful coexistence, but have you sort of ever analyzed it when you have one active hostile person?
Yeah, no. I have to say I'm ignorant about that whole area, but yeah, I would love to get educated on it.
It just seems to me that peaceful coexistence is a great goal, but put 100 people in a room, at least one person.
Yeah. Oh, definitely. I think one is would be lucky if there's only one who's hostile. Yeah. Yeah, but yeah, I personally, as I said, my background is not in security, but I would love to look at it. I think Ed Knightley, he has kind of looked at security from a denial of service point of view, in a multi-hop-ish. But
being able to, force a whole bunch of people into one band so you can watch them all at the same time, or something like that. It's not even just denial of service.
Yeah.
So.
That's the main reason it's not based on
I think policing is an important, who enforces that you are actually doing what you're supposed to do. And that's not part of this. And I think.
I was just sort of thinking as you were talking about like BitTorrent and things like that.
Yeah.
I mean, they do have a way, but I guess
it can beat enough.
there's some common goals. Everybody wants bandwidth and for a torrent, so there's ways to make it that if you cheat, you don't get the same bandwidth that you would if you didn't cheat.
Yeah.
That you would if you didn't cheat. So, I don't know. It just seems to me that should be something that's thought of at the very lowest levels. Like
I think you're right. But yeah, I think some of those concepts may apply for sure, but wireless is a little bit finicky compared to digital world. So it's hard to actually figure out. Actually they will actually mention these things are mentioned in a different way. That hard to figure out what other nodes are really doing, and how they're using it. And is it because if I think they are looking very good using more bandwidth, is it just because I have a good channel between them, or something else, right? So there is this randomness introduced into the system of measuring and by the channel itself, which is somehow you have to account for. But I think conceptually maybe some of these techniques would be applied to wireless settings too.
I just think it'd be really interesting in like each paper that you read if you also said, well, here's the theory, here's how it works, but also here's the worst thing that could happen if you have an active attacker and everything breaks
absolutely,
down. Sort of point that out.
A very good point, yeah. Let me hand it over to Patrick, because I don't want to eat in his time. I have a habit of speaking too much. For some reason it.
My name is Patrick Murphy. I'm a 5th or 6th or some very large number a year grad student at Rice that I hope to be graduating with a PhD next May. And so my work in the last 3 or 4 years has been on Warp. And so this is the platform that Ashu talked about briefly at the beginning that I'll talk about in much more detail here. So Warp, it stands for the Wireless Open Access Research Platform. And the whole sort of scope of the project can be summed up pretty well in this one figure that highlights each of the really core components of the entire platform. And so at the very lowest layer, we started with custom hardware. And that was motivated by the platform's overreaching goal of being able to design and build wireless networks with custom implementations at all layers in the networking stack. And so we wanted to be able to try custom physical layers and lay on top of those custom MAC layers and then interface those to either standard traffic sources over, say, Ethernet, or even implement higher layer protocols on the same platform where we could do IP and routing and everything on top of it. And so that kind of flexibility demands a custom hardware platform that exposes all of the processing resources you need to implement something as intensive as a physical layer, but then also merges it with real wireless interfaces. And so it's easy to go out and buy an off-the-shelf FPGA platform that has all the same processing resources that you need to build a physical layer, but one didn't exist that had that much processing tied in with flexible wireless interfaces. There wasn't a lot of interest in designing a wireless platform that wasn't adhering to a standard, because clearly we're not going to sell 1 million of these. And so we started with the custom hardware platform, which I'll describe in some more detail next. But then on top of that, we realized that we had to provide what we call platform support packages, implementations of glue logic, glue code, things that make the platform usable by researchers at any layer in the networking stack, so that if you wanted to try a custom MAC layer, you wouldn't have to design the PHY from scratch underneath it, or that you wouldn't have to design the interface to real traffic, Ethernet or IP, above that. And so the platform support packages are the things that we provide that make it usable out of the box to do networking research, customizations at any layer, where you don't have to understand what's above and below. But if you want to, it's all there. All of the implementations at all of the layers are open source. And so if you do need to customize the PHY to make some crazy MAC protocol work, you have access to it. It's there and you can change it in whatever way you want. And finally, laid on top of all of that are the research applications. And I'll talk about 2, one in detail in the slides, and then one is a demo at the very end that's running on the hardware over there right now. And then finally, all of those resources are part of the Warp repository. And so in keeping with the open access part of Warp's name, all of the hardware designs, our implementations, the platform support packages, our research applications, all of it's open source. which, as being a university, we have the benefit of being able to do that. It's all posted free under a nearly BSD license on the Warp website right now. And so starting at the lowest layer is the custom hardware platform. And at the heart of that is the FPGA board. And so this was the first board we designed in the platform. There's all sorts of the technical details about it. If anybody really wants to see the guts of it, the schematics are posted on the site, and you can go read about all of its resources. But the important part is the FPGA in the middle. And so an FPGA, it's a field programmable gate array. It's a chip with millions and millions of logic gates and flexible interconnect that can be programmed to implement really any logic function, any combination of logic functions that you want. And the FPGA that we use has something like 6 or 7 million, well, the equivalent of 6 or 7 million logic gates. And we can use those to implement any of the really high-speed processing we need for everything from the physical layer on up. And so the FPGA is really the only processor out there that is flexible enough to design say a PHY from scratch, and fast enough to have the PHY be useful in real time, where we can construct a network of these nodes that operate at tens and hundreds of megabits per second, not just doing offline processing on a PC where you get, say, a couple hundred kilobits per second because of the latency of getting data off to the processor. Then the second board is a much smaller board. It's a daughter card that actually plugs into the FPGA board. If we looked at the picture of the FPGA board, you can see 4 daughter card slots. It's the pair of white connectors arrayed around the FPGA. The 4 slots are identical. They can accept any combination of daughter cards. I'll show pictures of a couple of additional boards that we've designed. But the important one is the radio board. And so this board implements an RF transceiver, but its interface is just straight digital I and Q samples. It isn't tied to any standard at all. It really does just take the digital buses of A to D and D to A converters, drive them down to the FPGA, then up convert and down convert those signals and spit them out over RF. And so all of the physical layer processing, the creation all the way to the point of the waveform, has to be taken care of in the FPGA, and the reverse. As the radio receiver, it presents only raw samples that have come off the air. All of the processing has to happen in the FPGA.
Sorry, the FPGA is on this board, right?
Yep.
That makes
So the chip in the middle there from Maxim is the RF transceiver. It takes analog signals in and up converts them and down converts them. And the D to A converter is the big one on the bottom, and the A to D converter is the littler one up above.
AD and DA?
So the A to D converter is 65 megasamples a second, 14-bit, and the DAC is 16-bit and 100 plus megasamples. And so I just want to reinforce the point that we did use an off-the-shelf RF transceiver, the chip provided by Maxim, and even though they intended it for 802.11 type networks, it doesn't care at all what the waveform looks like. It's not tied to the standard in any way. You feed it a signal that's up to 40 megahertz wide, it will faithfully reproduce it at RF at your choice of frequencies in the 2.4 or 5 gigahertz bands, and then do the reverse for receive.
What's your frequency range around 2.4, for example? Like
So
it's the lowest you could actually get.
2.4 to 2.5,
Okay.
and then 4.875 to 5 point something is the top end. So they cover
2.4 minus 20 megahertz maybe, because you can, if I set my center right at 2.4, then, and I'm transmitting a 40 megahertz signal, won't it leak over 20 megahertz this way?
You definitely would. And the FCC would come knocking, but the radio will do it for you. And so actually the guts of the radio, you program PLL constants and things to choose the center frequency. And so you can tune it at 2.4 if you want, or 2.5.
Try tuning it lower just to see what happened?
No, we frequently tune, it would be possible for us to frequently tune it higher in the bands that aren't used in the US, right? Channels 12, 13, and 14 aren't allocated here, but the radio is meant to work in Europe and Japan where they are.
Can you change the frequency and bandwidth adaptively?
On the fly. So the bandwidth is controlled by the waveform generated in the FPGA. So you provide an analog, the radio takes in only an analog signal.
Okay,
So the FPGA, if it's providing samples at 40 megahertz, you get a 40 megahertz chunk. The center frequency you can tune on the fly. Ashi mentioned that before, that you can switch the center frequency on the order of faster than milliseconds. I think it'll settle in tens of microseconds. And the control of all of that, again, is in the FPGA. You're right. Either C code, we've written drivers and everything abstracting it up to that point, or in hardware, you can provide those commands. And so that's a picture of what would be a 4 antenna node. So there's the FPGA board on the bottom and then 4 radio boards populated in all the slots, largely for marketing purposes. We haven't built a 4 antenna MIMO physical layer yet. And so then in addition to the radio board, we've actually designed a bunch of other daughter cards that, the daughter card slot's very generic. It just provides just over 100 digital I/O signals routed back to dedicated I/O pins on the FPGA. And so really anything that you can fit into the form factor that's about the size of a business card that doesn't need too much more power than what the slot provides, you could build into one of these daughter cards and then exercise it from the FPGA. And so we built an analog I/O card, one that we can use to drive baseband analog signals in and out, which is invaluable for debugging physical layer stuff. We can look at constellations in real time being spat out of the physical layer on the fly. We don't have to try and capture samples and look at them later. There's a user I/O board, which again is just for demo purposes, LCD screen, buttons, trackball, memory, and we've got more in the works. These are all designed by students. So all of the boards there were designed by, all of those actually by undergraduate students as course projects in the lab. Then the final board actually is a clock board that we don't have mounted on these, but we have on some MIMO kits that we're working on in the lab that takes care of distributing very high quality clocks to multiple radios if you do need to construct a MIMO system. Because in a MIMO network, the physical layer almost always assumes that there's perfect synchronization between its own antennas, that there's no carrier frequency offset or sampling frequency offset between the different antennas in the transceiver. That's a fair assumption, but we had to design, of course, hardware to accommodate that. So then finally, we start to move up the stack, the stack of the platform a little to see how do you actually target the thing? How do you design for it? And so clearly, all of the processing that you want to happen on the node happens inside the FPGA. But there are actually a couple of different ways to get designs into the FPGA. You can either program the programmable fabric, that is, define the interconnect and the function of all the logic gates in the FPGA. But then also embedded inside the chips we used are PowerPC cores. And so the Xilinx chip we have actually has 2 PPC405 cores embedded in the fabric. And those can be targeted from standard C code. So Xilinx has a tool chain that you can write C code. It runs it through the standard GNU tool chain, and it spits out an ELF file that can be downloaded and run inside the PowerPC. And so this mix of being able to write software that exercises custom hardware inside the FPGA, which then exercises the custom physical hardware in the radio boards, is how we construct the full flow from Mac through the PHY and the FPGA all the way out to the radio interfaces. And so the state of things is clearly the hardware works. We've gotten it back in the lab. We'll see in a couple of minutes the demo that's running. The FPGA and radio boards were the first, and they work. We've got a whole bunch of other boards in the works, some daughter cards that have already come back, and extensions of even the FPGA and radio boards that we're sort of contemplating and working on. And that the hardware is out there. One of the goals of Warp, as it was described in the original NSF proposal, was to put it into the hands of other researchers, to have them be able to do some implementations of their ideas, things that aren't necessarily even our research interests, but that the platform is still capable of. So it's already in the hands of 4 universities and a couple of companies, and a bunch more have already placed orders. And we would like to sell as many as we could possibly make, but of course the support burden starts to be a problem. And so we're scaling it up slowly as we go. So then on top of the hardware, custom physical layers we already built that work. There's single antenna, there's multiple antenna spatial multiplexing, multiple antenna Alamoudi, all OFDM physical layers. And again, they're all posted on the repository. So these are all implemented and work, tested. The single antenna PHY is running over there at the moment. Then on top of those are implementations of medium access protocols. And again, all of these are implemented. These are in C code running inside the PowerPC, interface to the PHYs that we've already built. And all of it's posted online. So I wanted to walk briefly through 2 research examples. So these are the research applications that sit on top of everything in the platform and exercise all of the pieces that I've described to start to do interesting research that we wouldn't have been able to do without the ability to build it from scratch. The first is implementation of a cooperative communication system, which Ashu talked about briefly at the beginning of his slides, where you can think of it as a physical layer relay, where I'll describe it in a lot more detail. And the second is a multi-hop network link. You can think of it as a MAC layer relay, where packets are forwarded at the MAC layer, and that's the demo that's running over there. And so I'll describe it very briefly, and then we can go look at it actually running in the hardware. And so cooperative communications, it's a fairly old idea research-wise that at least was described in theory in the 70s and then revived with some new ideas in the 90s. But it still presents a whole bunch of unknowns, especially from an information theoretic perspective. But I like to think it has even more unknowns from a practical perspective. As best we know, people haven't tried to build this. And especially in a real-time, fully operational link, we think we're among the first. And so the system we wanted to build is really probably the simplest possible real cooperative communication system. So we worked with 3 single antenna warp nodes, acting, in this case, one as a source, one as a destination. The source has packets that it wants to send to the destination, but there happens to be a third node in the middle, the relay node, who's able to help in the transmission of the data from the source to the relay. So from the network perspective, all the traffic is unidirectional, flowing from the source down to the destination. And further, all of the radios are half duplex. We wanted to build it in practice, and so we had to use the radio boards that we have, which means nobody can transmit and receive at the same time. So the relay can't listen on one antenna, transmit on another at the same time for all sorts of RF reasons, not even just the radio chip itself withstanding. And again, our goal was to build it to execute all in real time. We wanted it to work standalone in the boards, no offline processing. We didn't want to have to rely on external computers to do the work. And so it's motivated by a standard spatial diversity scheme that it's a scheme that Al Amoudi came up with in the last, I can't remember what the paper was, early 90s, I think, where he described how to have one node with 2 transmit antennas, how he could encode symbols to send from the 2 antennas at the same time, which would improve the reliability of the link and avoid interference by the construction of the code. By the clever flipping of sign and conjugation of the complex symbols, it can guarantee orthogonality between the 2 spatial streams and thereby improve the reliability of the link. The receiver gets sort of 2 chances to hear the data, one from each antenna. And so we wanted to implement a scheme inspired by Al Amoudi, but using all single antenna nodes. And so rather than have 2 spatial streams, we had to break things into 2 time slots. So in the first time slot, the source sends what would be the stream sent from the first antenna in a 2 antenna link. Here I just call it stream A. It sends it to the relay, and in this case, the destination ignores it in our implementation. In the second time slot, the source sends the second spatial stream, and the relay turns around and sends a copy of what he heard in the first time slot. So his entire job in the first slot is to buffer what he receives. The second slot turns around and retransmits it. So an important point to note is that in the standard Al Amoudi system, there are 2 transmit antennas, a real antenna array constructed at one node. The goal of the cooperative system is to realize gains that are had because of the 2 antennas in a network with nodes that only have 1 antenna each. So essentially a virtual antenna array. Yeah?
Why are you time synchronizing the 2 transmissions between the sender and the repeater?
So actually that's 2 slides away. I'll actually talk about it in a little bit of detail. The details of the physical layer underneath it's based on the Al Amoudi OFDM system that we'd already built. And we used OFDM to help combat some of the synchronization problems that arise. In the sense that if the relay begins its transmission where it's not perfectly aligned with the second transmission from the source, the destination is going to receive 2 copies of a signal, or at least 2 signals that are arriving at slightly different times. And so one way to think of that is it's kind of like multipath in the sense that it could look like a reflection of the transmission from one of the 2 antennas in the Al Amoudi scheme. And so OFDM combats that naturally. It has built-in multipath tolerance because of the way the cyclic prefixes work and the spreading of symbols over time. So the synchronization errors at the relay, because of the relay, actually disappear in the multipath tolerance in the OFDM PHY. And so the original Al Amoudi PHY that we built and then the extension of it for the cooperative stuff, it borrows from the 802.11 standard for things like the frame format. We figured the standards committee came up with good frame formats, training symbols, preambles, and that. We reuse them exactly. And so the important parts that will show up in the timing diagrams in the next slide are short training symbols that come at the very beginning of the packet that are used to help the AGC at each node converge. Long training symbols which are used for fine symbol synchronization. It's a long sequence with really good autocorrelation properties that can be used to find the exact instant that is the FFT frame starts. There are dedicated channel training symbols that come next. And then finally, the spatial streams, the payload data itself run through the Alamudi code. So in the first time slot, the source sends a packet constructed in a special way that has just the short training symbols as a preamble that allows the AGC at the relay to converge, but it's lacking the long training symbols. I'll show why in just a second. And then for the payload, it contains a training symbol and the first spatial stream. Now, the destination technically hears that transmission, or it would if it was within range. But for the purposes of this system, when we constructed it, where we really wanted to explore the cooperative aspects of building a system like this, the destination intentionally ignores that transmission. And it does it by not having a long training symbol in the preamble. Remember I said the long training symbol is used to define the timing of the packet. If it's not there, a receiver just decides the packet was detected in error, gives up, and moves on. So in the second time slot, the source sends a new packet construction. Again, it has the AGC symbol at the beginning. This time it has a long training symbol, which allows the destination to receive the packet and define synchronization. It has a channel training symbol that is offset in time from the one that the relay is about to send. And then it has the second spatial stream. So when you sum those two things together, you end up with a fully constructed Alamudi encoded packet sent by two different nodes, received at the destination, which achieves the goal of having it work just like a 2-antenna transmitter, 1-antenna receiver in a standard Alamudi system.
The point of the relay actually doesn't demod the bits at all, so it just stores it and forwards it, so it didn't even need the training sequence.
Right. It needed the short training sequence in order to converge AGC, but it stores the channel training sequence, and that gets retransmitted with the payload so that the destination can actually estimate the compound channel source to relay to destination, because that's what the payload got exposed to. And so the results, after building the system, we ran it through the normal performance tests of what kind of bit error rates can we get, comparing the relay case to the case of the exact same nodes, exact same configuration, but turning off the relay altogether. And so in the first case, we said let's not have any power constraints. The relay has its own power source. Whatever power it uses doesn't detract from the sources. And so you can see right away that turning on the relay, at least in the configuration of the nodes we had them for the test, gave a huge performance increase. Bit error rates dropped pretty significantly when the relay gets turned on. Now, intuitively, this makes a lot of sense, that even in the corner case of the source not sending anything in the second time slot, the destination still gets a lot more power from the relay than it ever would get from the source, simply because it's closer. So a lot of this gain is just straight SNR gain, less path loss. It's a real channel. I don't know what the channel coefficients were. Right. That's what the setup looked a lot like that, antennas placed in an office.
It was relay channel for 25% of the time. That's the rule of thumb. Real channels.
But one other comparison we can make, and it's sort of an interesting one, is what if there were a total power constraint? If we said that the total transmit power for the entire system had to be constrained so that when the relay turns on, the source would have to back off on its power to have some same total. And so we can actually get insight into the results from that from the same plot by finding 2 points on the plot of equal total transmit power. So the first is the case of the source sending all by itself, no relay at all. Then finding the equivalent point where the source power plus the relay power is the same. And again, when we find those points, we find there's still a fair bit of gain. Again, intuitively, a lot of it is the SNR gain, the path loss, dropping from the relay to the destination. But the gains are real. Yeah?
Would it be possible to put the relay at the same distance than the original center, and then you would kind of filter out that gain from just because it's closer?
Right, but if they're going to be co-located, you may as well build a MIMO transmitter. But absolutely, I would expect a lot of these gains would disappear if you were to move the relay right next to the source.
Okay, just to get a maybe cleaner result, or
right.
I don't know.
Well, certainly another set of data points, yeah.
Another thing is that typical axis which is plotted in relay result is distance of relay from source.
Okay.
So that's a parameter. So there's some good locations and bad locations.
Then the final plot just compares what happens if you adjust the rates at the nodes. If you switch from BPSK, so 1 bit per symbol, to QPSK, 2 bits per symbol, you can see still that the gains are significant by any combination of modulation schemes. So I'll stop there for any questions about the hardware, the platform, the cooperative results that are actually fairly new, our newest application, before I jump into just 2 slides about the construction of the demo, and then we can go look at it running.
The demo, yes.
Yeah.
I have a question about the hardware itself.
Sure.
Would it be? Can you compare your platform to other platforms out there? Like, for example, TI came out with the SDR platform as well.
Right. So they're
Interested to know the differences.
So that, I think you're talking, it's the Leartech small form factor software-defined radio, about yay big, 3 boards stacked up. Yeah. So that one was designed. First of all, it's a single antenna node, just by definition, and it doesn't, as best I know, doesn't have the ability to add extra antennas to it. And then the other one is that the processing resources there are split between a powerful DSP and a medium-sized FPGA, and that's much more a philosophical debate than a technical one about whether that's a good thing to do. Clearly, I erred on the side of let's put as much programmable logic on the thing we can and leave a total lack of DSPs on the board.
Have you looked at the USRP?
So that one is almost orthogonal to this in the sense of the kind of things they want to design, in that at least the USRP version 1, it does almost no processing locally. It decimates and interpolates, filters in the FPGA, but it can't do any kind of real physical error processing in the chip that they've got. Now the next one, that they've got a Spartan 3 coming out in the USRP 2, even that one is a tiny fraction the size of the chips that we use here, because Matt wants to sell it for less than $6,000. Their goal is to do offline processing. All of it's offloaded to C and C++ on implementations in C and C++ on a PC, which is great for iterating quickly on the design, but makes a demo like this really hard. Nodes standing alone, acting as network interfaces for other computers. Sure. Well, and they made the conscious choice of use a small FPGA and offload the processing for the design simplicity and the expense, for sure.
I think I remember reading the USRP too. They did want to play around with MIMO stuff. So.
Yeah, and actually Matt just yesterday posted some details about it. It's a Spartan 3 1000. It's only got 1 daughter card slot. And if you want to do MIMO stuff, I think you have to hook multiple of the FPGA boards together to extend out for the number of antennas.
Week, so I'll talk to him about it.
Okay, so then the second application is actually deceptively simple. And so we're trying to construct a link that looks like that, just streaming video from one laptop to another. But we want to do it by tricking the laptops into thinking they're directly connected by a wire, but in practice, their network link is constructed out of warp nodes. And so the demo that runs, one laptop is connected by Ethernet to the node on the right. It's sourcing streaming video, just VLC producing UDP traffic. The first warp node accepts that traffic, transmits it out over the air using the custom MAC implementation, the custom physical implementation, spat out through the FPGA over one of our radio boards. The middle node receives that. Then at the MAC level, again inside the PowerPC, turns around, readdresses the packet to the third node with the wireless MAC address. Then the third node receives that packet, strips off all of the wireless header information, reproduces the original Ethernet packet, spits it back out over the wire, and the laptop receives it as if it had come over the Ethernet connection. So it is a wired to wireless to wireless to wired bridge, where all of the wireless stuff in the middle is warp, all of it built from scratch. That's the last slide, and we can go look at it running over there unless there are any other questions.
As far as your open source repository, is OFDM really the only thing that's there? I haven't looked.
Right. No, so there's 2 different OFDM models, the Al-Moody implementation and then the MIMO multiplexing model.
But do you have any other modulation types that you've been... that have been
We concentrate only on OFDM for our stuff. But the model itself supports all kinds of modulations, everything from BPSK up to 64 QAM. All of them work. We've done the tests over the air.
And do you actually have implementations of those?
Oh, sure.
Okay.
This is QPSK at the moment, but we can do any combination of modulation schemes per subcarrier on the fly. The benefit of designing it from scratch, right? We don't have to beg Atheros for access to the firmware. Yeah.
So on the fly, you mean you change the use partial configuration to change while it's running, or?
Sure. The choice of modulation scheme is defined per packet. So the MAC can say, let's use this allocation of subcarriers with these modulation schemes, and it'll produce a packet with that information and send it out. And the PHY will faithfully decode it and spit it, reproduce the packet at the other end. totally non-standard, right? We weren't aiming to rebuild 802.11 at all. A lot of it's inspired by that because the committee did a good job of defining a lot of it, but we wanted way more flexibility than the standard part would give you.
You have 802.11 implemented then?
No.
There's just a lot more.
I mean, most of the physical error processing for 802.11 is already there. All of the OFDM processing, the synchronization, we're close to having a Viterbi encoded version of it up and running. But to get from this point to a fully compliant, put a Wi-Fi sticker on the box, it's a huge project, and it's not one that we're about to undertake. Certainly the resources are there if somebody wanted to build it.
I was thinking more along the lines of just actually watching someone else's 802.11 traffic using this, but
you'd have to implement the full PHY to get that to work.
Yeah, and you can do that with commodity hardware.
Right.
Anyway, so.
Which is one reason why we're not about to put the effort in to design it. Or to build it, it's already designed. Okay.
All right, let's thank Professor Saboa and his student Patrick for the excellent talks. That was